everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are going to get back into the world of vectors, and maybe hopefully we'll get into a little bit of linear algebra today. Like this morning I was basically just, I just felt like I would pick up something on linear, basically look up some stuff on linear algebra, and kind of got inspired because I just felt like I did look up the difference between basis vectors and unit vectors, and I realized that I didn't fully understand them until I actually had to go back and kind of review on exactly what they were, because I had basically it's like those times when you feel like you learned a little bit about it, and then you felt like you kind of know, I think somewhat of the basics, but then when you dig deeper into it, you kind of feel as if, oh wow, there was something you were missing. That's the experience I felt when I was doing it. So when I was trying to read up on unit vectors and stuff, but that's basically what I experienced this morning, and I thought why not just get back into some linear algebra. All right, so we got a physics problem here, I think. So let's actually do that. That actually looks pretty cool. So let's copy that. But how you guys doing today? It's Tuesday. Hopefully you guys are having a good Tuesday. You're almost at the middle of the week, so give yourselves a pat on the back for that. Let's expand this like so. Okay. Let's see. Okay, so what is the problem we're dealing with today? In mechanics, the work done by the force F acts over the displacement dr is defined as a scalar product between the force and the displacement. So, okay, so it is a dot product, or in this case, it looks like it's supposed to be yeah, just a dot product, because for some reason I was going to say it's going to be like a divergence, but I don't think that's what we're going to be aiming here for. How much work is done by the vertically downward force of the Earth's gravity? I'm guessing they're basically saying the magnitude of the force is m times g, where g is the acceleration of gravity on a car with a mass of 1,200 kilograms. Okay, so let's just write what we know here. So just raise this up a bit. Alright, so we know that the mass m of the car is kilograms. And we know what g is if you've taken physics before. So g is 9 meters per second squared. And the car is moving 50 meters down a hill whose surface makes an angle of, oh, okay. So the distance, or at least dr in this case, is 50 meters. The car moves down a hill whose angle, so let's put that as theta, is 20, is 20 degrees. It's 20 degrees below the horizontal. So I'm guessing, with that in mind, so the car is going down a hill. This is supposed to be 20 degrees this way. force here is the mass times gravity here. Luckily we have our calculator with us. And I think we have to rewrite these like vector components, so the mass is a scalar, so it's just that the force is a whole nother matter. So the force on this is newtons. And that's in, we'll just put that as a J, in the J direction, just to make it more convenient. And this one is going to be 50 meters. Well, so in this case, we're going to have to write this like a vector now. So I think what we have to do is put this as 50 meters cosine. We should put like -20 so we know that's below the horizontal. So, and then plus -20 J. Okay. So I think at this point, because since it's below the horizontal, I'd rather write it in the other way. So instead of -20, be 340. Like that's just an alternate, because basically it's like 360. 360 minus 20, so I'm just leaving that up here just in case if it feels uncomfortable. Okay, so we got the mass, we got the force, so the force is basically the dot product of this, so that means this would have to be multiplied by this, plus, and then basically we have 0 for this one, so this one's going to be 0 for the work done. So the work done in this case we have to like make it negative so that way we can have a positive result, because this is going to end up negative and this is going to and this, like, because the force is basically just that much on the earth, so force is equal to, well, the work done we'll just leave it like that, so that'd be joules, I think. I think the unit we work with work is joules. I'm just gonna quickly Google that to make sure. SI unit work done. Yeah, it is joules. because we got newtons, and this one would be meters, so Newton meters, and that's basically like when we think of work, it's usually like newtons times the distance, which is meters. So yeah, I think that should work out. So oh yeah, we probably should get the answer guide out. Chapter 2 problems. And this is number 11 for 2. Oh, this is one of the last ones. Because the way they laid it out, it kind of seems straightforward. It's just that you have to like know how to write out the distance here. Because the distance, it says it goes 50 meters down a hill, which is the vector itself. So I'm thinking 50 meters is the magnitude, and you want the actual distance, because like if it's like 20 degrees, then basically we have to take the angle into account. Hopefully, because we got like 201,313. So, as much as I know, as much as I've learned about work in physics, I feel like the way I was thinking is kind of like, it feels right, but at the same time, I just want to make sure. Because it feels like, you know, I could be wrong in somewhere, so let's just see. So they did, yeah, that's the distance. Oh, they did the cosine method. Well, we did everything correctly. It's just that, oh, that's interesting. I mean, we did everything right. I mean, like, the way I was thinking was, like, I guess correct in my mind, but, like, seeing the way they did it, it just seems probably a little bit more concise than what I was thinking. Because I usually don't use, like, cosine when I do the dot product example. I mean, not example, but doing the dot product itself. I usually do it the most basic way. Let's see. So, oh, okay, I see why they did that. So basically, cosine, you have to act like this angle here. Like, so this is like that vertical. I think that would be like extra. It's kind of like extra work, though. I mean, like, looking at it, I mean, we did get the correct answer. It's just that, I guess, like, the way they did it was a little bit more concise, but it felt like it was just too extra for me. But maybe doing this is a little bit too extra for someone, I think. But, I don't know. You guys decide. Because for me, I think my method just felt more... It felt more fluid to me, but then again, it could be a little bit more messy because the way they wrote it is like, kind of like more, it's more clean. You guys be the judge. Okay, but I think we got that right. So, I would consider that as a win. If you guys are watching this on YouTube, you know, you can put in the comments and like basically say that mine is not elegant, and I accept that. What is the next one? Okay, so let's just... I think we might as well just do 12 because I think that's the last one of this whole thing. that... Imagine trying to turn the head of a bolt by pushing on the handle of the wrench. The vector torque exerts by a force you apply. I'm so used to this type of problems because since I am familiar with cross product and dot product, that's so I'm wondering if they're gonna make you do the sine version of this. So we got the equation for torque, where r is the vector that points from the point of rotation to the point of the application of the force. If you push a handle with the force of 25 newtons, so I guess we can write the force, or at least the magnitude of the force, so that way we don't get confused. The distance from the point of rotation, that's 12 centimeters, so I guess we'll just write D. The distance of rotation is 12 centimeters from point of rotation. In what direction should you push to maximize the torque of the bolt head? If you push in that direction, how much torque will be exerted on the bolt head? Okay. I'm guessing R is supposed to be the. I'm guessing this is supposed to be the magnitude of R. 12 centimeters from the point of rotation. So what we can imagine is that, let's imagine this is the bolt head. I don't know what it's on. Let's imagine it's like some sort of like block of wood or a tool or something. And so the distance from the point of rotation is 12 centimeters. So let's just pretend you have like some sort of like wrench or something, and it's not to scale, but let's just pretend it's like 12 centimeters, something like that. Yeah, this is not a really great drawing, but let's just imagine that. Or maybe I should write it like down, like more down here. Make it a little bit more feasible, if that's the right word to use. Okay. So imagine trying to turn the head of a bolt by pushing the handle of the wrench. Okay. The vector torque exerts a force you apply. So let's just write the equation. So that way, so this is the torque, R cross product of F so we have 25 newtons for that. So the bolt itself is just basically like, so I'm guessing they want us to do the cross product as the sine version, so it's like magnitude of the force, sine of theta times the norm. Well, it shouldn't be a unit. I don't think it's a unit. Is it a unit vector? Maybe it is a unit vector. I don't remember. I know there's a random vector here that's supposed to be like the normal vector that goes perpendicular to the other two. It's given by the equation. If you push the handle of the wrench with a force of 25, so maybe I should draw this from a bird's eye view. Maybe that might be a little bit more better, because it seems like they want us to look at it from a bird's eye view. So let's imagine this is like just make it a like that. And then we have the wrench here, like that. Let's just make the bolt like that. And then this is 12 centimeters. And if you push the handle of the wrench with a force of 25, so I'm guessing we'll push it that way, 25 newtons. That's the force. In what direction should you push to maximize the torque on the bolt head? If you push in that direction, how much torque will you exert on the bolt head? Well, usually like I think this comes down to the right hand rule, where it's like you have to push it, like either you push it to the right or you push it to the left. If you do it from the left, like right now I'm sticking my own right hand just to show. So if you push it to the right, to the left, then basically your thumb will go up. But if you push it to the, because basically the right hand rule is that you take your hand and then you stick your fingers towards where you want your fingers to curl. So if your fingers curl towards the left, you see that your thumb sticks up. But if you try to curl your hands to the right, then basically your thumb will be down. So the one thing I'm wondering about this question is that do they want us to take out the bolt, or do they want us to screw in the bolt? That's why I'm like kind of rereading this question, because well, we don't have an angle, so I don't think we have to worry about this. So this is the distance from, and there's nothing in the, I don't think there's anything to be concerned about in the y component, or the j component, I should say. So in what direction you push to maximize the torque? So I'm guessing to make the, so basically to give more, I guess like more, maybe more tightness. I think that's why it says maximize the torque. Because if you reduce the torque, I think it's basically making the bolt looser. If you push in that direction, how much torque will you exert on the bolt head? Well, they always say in like, I think like, I don't know where this expression came from, but I got it from like, I think an online physics course that I was like learning from like way back. They say that righty-tighty, lefty-loosey. So I usually go by that rule. And with the right-hand rule, you can see why, because it's like if you stick your fingers like out, and then you curl your fingers in. If you curl your fingers in from the left to the left, you see that your thumb goes up. But if you curl your fingers towards the right, you see that your thumb goes down. So the direction would have to be, you have to do it from the right. So you have to like actually turn it towards the right. Because what I'm thinking is like, the way it looks like is that do it like this, and then the distance from the now with this in mind, that's just a little free-handed diagram. I don't know if it will help us, but sometimes I like to draw small stuff to actually like get my brain working. So now the question is that do I use an angle in this case? Because I think that would be kind of like too excessive. if we try to get an angle from these two vector components. Okay, so let's just say it's like two-dimensional. So we have I and J here. So for the J side, we'll just have 12 here, and then we'll have 0 here. And then for the force, I think what makes it tough is that, like, because you know the system. For me, I know like we're familiar with, you know, like tightening a bolt with a wrench. The one thing that I think I'm kind of confused about is, like, obviously when you turn a wrench, it goes into a circle, and you know that there's going to be an angle. There's going to be like an angle, whether it be you know, like 30 degrees or 9 degrees or whatever, what have you. So I'm trying to think about how I can write the forces and as like purely components not involving the angle. Like, a part of me is tempted to basically take the the inverse tangent of 25 and 12. Because I just don't want to make an angle that is there, like that just pops out of nowhere. That's the one thing I don't want to do. Because if you did take, let's just say you did do that, right? Then 25 over 12, it says that it's around like 64. 64 point, let's put 64.4 degrees. Now, because we know we have to turn this, and you know, with like 12 12 centimeters away from the, you know, the central point here, the question is that wise to do so? I mean, it will probably, like, it will probably make a lot better way of so if we have it like here, but then again, because I'm like, now I'm thinking about like how it looks like from in the page and out of the page. So because, like, since we're looking at it a more bird's eye view, we wanted to like turn it to the right. Yeah, so yeah, this would be the right. Like, if I'm sticking my hand out, I know you guys can't see me doing the right hand rule around me, but if the bolt is in the page, we wanted to make sure it goes on into the page. So the way the direction would look is that it's not pointing this way. It would actually have to go down here, because that's actually turning it to the right here. Because like if I use my thumb, the angle would basically like just cover that. So it would have to turn the wrench like towards us in that way. If you push in that direction, how much torque will you exert? So I think we have to use this angle, but it's gonna have to be the negative version of this angle. It's gonna have to be below the horizontal. So let's just try this and like see how it works. So I think the formula we can use is the one that I was thinking about. Sine of, let's say, -64. Well, actually, we should just leave it in a general case with the unit vector there. Okay, so. We have 12 centimeters. Oh no, maybe we should convert this. Yeah, we should convert this. Because I forgot it's 12 centimeters. We want it in meters. That probably might make it better. So we have 12 centimeters times so 100 centimeters to make 1 meter. So meters. Yeah, so I think that would be much better. Okay, so now 0.12 meters times 25 newtons, and the sine of negative 6.4. So the torque, based on what I calculated, it says it's like -2 point. We'll just put -2.71. Because I think if you're just thinking of torque from perspective, it's like because I think it's because it's going below the horizontal, that's why it's calculating like a negative number in this case. Because we're also doing it from a negative angle because it's below the horizontal. The one thing that's kind of like making me feel like I'm not sure of my answer is because one, we got a negative number, because I think the reason why we got that negative number is because it's in a like it's below the horizontal. We have to actually tighten the bolt. plus the torque is supposed to be going in a perpendicular angle from the force and the distance. So my concern is, because I know a torque, it can't be like negative, and I know it's negative because of the angle we chose. I just want to make sure that, is that the right way of thinking about this, or is it like... Because the direction we want it to go towards is like, we want it to be turning towards us to the right. Because we want the bolt to go inside. But I don't know if that's the right way to phrase the answer. I probably got this one wrong, but let's just see how it turns out. Yeah, they did the same thing I did. Okay. Okay, yeah, this is what I mean. Yeah, I totally didn't understand the question here. Cause let's see what they answered. Let's see, make the drawing. Maximize the sign. Yeah, this is what, like, because usually when I read it, when it's like maximize, I kept thinking about like the bolt. I wasn't thinking about like the values. So that was my error of judgment there. Because I think for me, it's like whenever I work on like physical problems, I keep thinking more about how it will behave physically, but I always forget that we're dealing with actual numbers here. So I sometimes forget the mathematical behaviors of the system. But that's something to keep in mind. Like, you know, hopefully my own intellectual pitfalls or become your lessons, because maybe you guys are like trying to phrase this, probably have the same concern, and you just didn't know how to phrase it to your teachers or something. That's probably a good way to phrase it. It's like, I understand the physical system, but when it comes to actually applying the mathematical behavior, that's when I lose track. So to maximize it, we have to have 90 degrees. So, I mean, we did get the values right. It's just that we didn't get the angle correctly. Yeah, because I think I think they wanted us to maximize it, and the only way to maximize it is to think about the angle. So that's something we probably have to practice on. So this one was, well, we learned something though, because like we learned that we shouldn't assume what an angle is because they didn't give us an angle. So that's something to keep in mind. So to maximize it is just basically get it to 90 degrees, because sine of 90 degrees is 1. So basically it will give us the maximum force there, which makes sense. So my flaw was basically not forgetting the behavior of this sine theta. And I think like that's how you learn physics better, because it's like, oh wait, there is a mathematical behavior here, and like that's the thing I forgot about. I wasn't thinking about is the mathematical behavior. It's basically how sine behaves as a mathematical construct. So that's something to keep in mind. And this is cross product. I mean, we got the setup right. That's the one thing. It's just that we assume certain things that we shouldn't have. I mean, we did get the conversion and everything. And we did know what to do here. We just didn't get the angle right. But this one was a pretty tough one. I had to actually think about it for a second. So maybe, let's see if we can find let's see if we can do like some physics problems actually, because I feel like this problem was pretty good. I feel like I want to do a physics problem involving the same concept here. So, hey Sasha, how's it going? How was your day going, my friend? Maybe university physics. I think that should be fine. Okay, let's look for mechanics. I want to look for torque. More problems involving torque. Potential energy, work energy. Dynamical. Here we go. So let's see if we can find some more example problems with torque in it. I think that will help solidify our knowledge of the cross product a little bit better. Oh, here's a problem we can practice, and it has like... Okay, so I'm going to try to... Let's see. I want to see where the question ends, but I don't want to look at anything else. So let's take this. Okay, let's copy that. I'll just drag this down here. Good. Watched a bit of, wow. Exact, 100 integral challenge. Dang, that's crazy. I was actually doing integral by parts, integration by parts yesterday. Okay, here we go. Let's take a look at this. To loosen a pipe fitting, a weekend plumber slips a piece of scrap pipe, a cheater, over his wrench handle. He stands on the end of the cheater, applying a full 900 newtons weight at the point of 0.8 meters from the center. The wrench handle and the cheater make an angle of 19 degrees with the horizontal. Find the magnitude and the okay, so it doesn't say below the horizontal, so it's over. Find the magnitude and direction of the torque he applies to the center of the fitting. Okay. He's at 30 now? Wow. Crazy. I actually probably should do something like that. Just to do integration exercises, just so I can get used to like integration techniques. But 100 integrals, that's crazy. But if it were me doing it, I'd probably end up flustered at a couple of them, because I'll be like, oh my gosh, I don't know how to do this. Or I would have to like basically, I want to Google certain things and I forget. Because yesterday I think I had to Google a trig identity. And I'm like, no, that's not right for a challenge. I have to actually know my stuff. Okay, they said that there was a diagram, right? Oh yeah, here's the diagram, so I'm gonna try to copy this diagram they showed here. So, like this. I'm doing my best not to look at the solution. here. Okay. So 9 degrees above the horizontal. Okay. Can we flip you? Yeah, there we go. Oh, well, doesn't look like all the numbers are backwards. Because I don't want to do this on the second quadrant, but so we got this here. I wish they drew it the opposite way, but that's okay. We're gonna have to deal with it. Okay, so torque. Let's remember what. So torque is the cross product of the force. Okay, which can also be the magnitude of these two. Sine. Okay, so it's 19 degrees, so we know what theta is with the horizontal, so yeah. So we know the force, or the magnitude of the force, I should say. 900 newtons, and the distance is... Alright, so I guess they want us to calculate this. Hopefully I can do this, at least. And sine of 19 degrees. And then the torque comes out to be 240 newtons meters. Now, is that the answer that they get in this book here? Or do I have to do some crazy conversion technique? Yep, I knew it. I had to change the angles. Should have known it wasn't going to be that easy. That's the reason why I wanted to flip this, because like I always hate it when they flip it in the opposite direction, and then I'm like, oh wait, do I have to convert? And I guess I have to convert angles. Let me see here. I mean, we got the setup right. It's just that getting the angles was not, the angle was wrong. Actually, it's kind of funny because both problems I actually ended up getting the angles wrong. But that's how you learn. That's how you learn. And I keep these in the streams as well as the videos on YouTube because maybe it'll be like a good learning experience for you guys. Let's see. I'm just trying to see how they did the angles here. So I'm guessing let's see, it's 9. So they got 109. Which is that from 180? So 180 minus 19. 61. So that's like 71 degrees. Oh, maybe they did it to like reduce the, because it's supposed to be between 0 and 90. I think they did that to like kind of reduce it. Because I'm like looking at this part, and I'm like wondering how they get to this angle. Let's see 19 degrees. Alright, so vector, the angle between them. So this is the distance. Oh, okay. This is probably why I went wrong. So basically, I forget that it has to be the angle in between the distance and the force. I was thinking about the angle between the horizontal and the... Okay, yeah. I have to remember that. See, this is why we have to practice, because then you realize, oh, that's my blind spot here. Because sometimes when you're given an angle, so if it's like 180 minus 90, and then you then you get 71, okay. Alright, so that's something to keep in mind. So, usually like when it's these type of problem, or usually when I struggle with a problem, it's usually some detail that I didn't think about beforehand. But I think everybody is like that. It's like, and then like people get flustered and they're like, yo, why am I not doing this right? What's wrong with my thinking? And I think for me, it's like if you give me like an equation and you tell me how to do it, and then I basically just do it, but then I forget to analyze the behavior of that said problem, or the said parameters of the construct that I'm working with. So let's see if we can do some problems. So this is 10.1. So let's do some problems involving more torque, so hopefully we can solidify it in our head. Calculate the torque, magnitude, and direction about the point. Okay. I mean, this one seems like a simple one. I mean, a simple one we can try, you know. Because even though a problem looks simple, that doesn't mean it is simple. And it is one dot, so that means it's going to be like one that you have to apply the principles to. So that's not right. So I'll just write a reminder. So the angle between the force and I'll just write lever, because I think that's what I learned when I was like when I was learning physics at algebra-based physics. We'll expand this. At least we're doing some physics problems. Okay, you guys can see. Okay, I'm kind of I sometimes worry that you guys won't be able to see what I'm putting in. Let's see. Calculate the torque, magnitude, and direction about the point O or 0 or the origin. So we have a force and we have a lever. Or a rod. It says a rod here. In each case is F of the rod lies on the plane as a length. Okay. So we have 4.0, and the magnitude of the force is 10.0. So we have to calculate it for each of the cases. I mean, for A, since it is 9 degrees, I'm guessing this arrow is like the angle from like and then the force is like going up. Like, so if you push it up and it's like 90 degrees perfectly, then basically you're just gonna have the maximum. So it's just gonna be like 40 Newton, 40 Newton M. And we have to and we also have to say the direction it's going. So the direction it's going to go is basically just going to go like because I think it's the central point O. So we have to think of it as sort of like a screw. So if it goes in, so we go up, we go this way, and then we go up like this. Oh, maybe the angles tell us which direction to move our hand around for the right hand rule. So that means if we have the rod here and the force is going this way, then if we curl our hands down 90 degrees, then that means the direction of the O point is going to be pointing towards the, we'll just write towards us. And for B, we got a force that's 120 degrees. So that means we're gonna have to use like sine. So that means we're gonna have to use this method. So the angle is now, that's the angle between the forces, so the force and the lever. So I think that should be, so we have meters times 10, but then sine of 120. That would give us 34 point, let's put 34.6. And at this rate, the force is pointing this way, and we're going down this way, so it's still pointing towards us, the O point. The O point is still pointing towards us because it's going in it's going towards the left, the arrow, the angle, I should say. Okay. Let's bring this up here. All right, for C. So we have theta is equal to 30 degrees. Okay, so okay, so like the next one they tell you like a new distance. I'm like, that's really interesting. And basically now the force is actually applied to the central point here, which means that the distance here is practically 0 in this case. And if you apply the force here, so let's just do C first. So we have sine of 30 degrees. Should put the torque here, or tau, I should say. This one's 20 newtons. So just give me one brief second because I want to get like all the problems we're working with here. So this is chapter 10. Oh, I thought torque would be like much further down. So this one is exercises. Okay, so I'm just gonna pull this down here, right here. So that way we can just easily access those problems. Distance here is going to be 2 meters, because it's like 2 meters away, because it's like 4 meters, so it's like if you take half, like if you minus 2 meters from 4 meters, it's going to be 2. So now we're given so the force from the, so theta is going to be 60 degrees. The force doesn't change, so the force is still going to be ten newtons. So sine of 60 degrees. So the torque, or at least the magnitude of the torque, 17 newtons. And then E in this case is just pointing to there's no different distance, so that's 0. So practically I think the torque is going to be 0. Because there's no real distance to actually measure there. So I think the torque is going to be 0 in this case. Now this one, the distance is there, and the force is being applied to it, but there's no angle here. So I think that one's going to also be 0. Because there's no real angle made by the arm. Now, let's see. Yeah, because like the torque calculation in this case, if it was the force was pointing down. So we have the force pointing this way. Like, I mean, it's pointing like slanted, like downwards in D here. So I'm trying to position my fingers towards where the force is pointing, and then with the 60 degrees, then I think the O point is going to be pointing towards the page. Now if you point it this way, like in E, the thing of it is that there's no distance there, and mathematically the way I look at it is that, like, because it's 0, because we don't have really a distance here, we just only have it pointing towards the the origin point. So there's no real distance there. So let's just take a look, see what we get. Yep, we got that one, 40 newtons. Yeah. 20, yeah, I think we got 20 for that one. Yep, we did get 20 for that one. For D, let's see, 17.3. Yep, 17.3, we got that one, okay. Now for E, yep, 0, that's what we figured, and 0 for that one, okay. Okay, so now I think we're pretty good at the basic way of thinking about torque. Now let's get into a little bit trickier problems. So let's just do 10.2. Luckily these present pictures. I actually am liking the pictures because it actually makes me visualize it better and I don't have to make crude drawings. Paste. Okay, so calculate the net torque about O. The point O for the two forces applied as in the figure. The rod and both forces are in the plane of the page. Okay, so we have two forces. Okay, this is going to be a little bit more interesting. So force 1 is, and I think we'll just label like distance 1 and distance 2. So I think we'll put a theta 1 here. So theta 1 is basically just 90 degrees. So, oops. It's just nearly orthogonal to it. The distance here is 5 meters. 5 meters. Okay. For the second force, I think we're gonna have to do these like separately. So they want us to calculate the net force on the point O. Okay, so what I'm guessing is that we're going to have to add all of these together. The torques, I mean, like the different torque values we calculate. Distance, so 12 newtons, and the angle in this one is 30 degrees. Wait. Because the force is kind of coming out in this one. So I'm wondering, is it 30 degrees? Because it's pointing this way. It's pointing out of the rod. But I think the distance is still like 2 meters. The thing is that because they divided these two sections here, I don't know if the force here, it makes a unique point here. That's the one thing that I'm concerned about. We'll just put 30 here for now. I'll be right back, guys. Just give me 1 second. Alright guys, I'm back. Sorry to keep you guys waiting. Alright, now I think this is where it's going to get a little bit interesting, because now we have a more complicated problem. So, now the thing is that I don't know if this new point where the force is popping out, F2, I don't know if like the tail end of this vector, I don't know if that's supposed to be the origin point, like the origin point of the torque of F1. That's the thing that I'm concerned about. Because we want to know the net torque on O, so... The thing is that F2 is not pointing on the distance, but then again it's still the force like between, so maybe it doesn't matter. But you have like one force is actually pulling up and the other force is pulling down. So when you think about it, it's kind of like behaving in a way where it's like kind of like going up more instead of going down more, because like F1 is much is less than F2. So I think we might have to subtract them, because they're going in opposite directions. Let's give it a try though. So let's put the summation of the torque so let's make it so that F2 R2 sine of theta 2 minus F1 R1 sine of theta 1, because one is pointing down and the other one's going up, so I feel as if because the direction of the force, I feel like it matters too. That's the one thing that I'm concerned about, because if it's pointing in the direction where it's like kind of heading towards the origin, that's the one thing that I feel as if might play a part in it. I mean, Maybe it should be the reverse, because when I think about it, sine of 9 degrees is going to basically give us the maximum we can get for this. This one, I think it will just give us like a little bit, so because it's at an angle less than 90 degrees. So maybe we might have to switch these around. So maybe we'll add a plus there. No. I think we're gonna have to rewrite this. We'll do it like this, and sine of theta 1 minus f2 r2 sine of theta 2. So if we did all the numbers, it's 5 meters, sine of 90 degrees, and minus that from 12 to and sine of 30 degrees. Turns out the torque because I think the torque is also the cross product, so it has to be the vector at this point. So if you calculate the net torque of it, so we started with 8 newtons. So the first part, basically this one gave us 40, but then we have to reduce it by, let me see, 12.2 and sine of 30 degrees, 12. So you had to reduce it by 12. Now the thing of it is this the correct way to think about it though? Because the one thing I'm concerned about is that I don't know if it treats this area as like some sort of central point. But that's something that we're gonna have to like actually learn if we see the answer. So let's see. So we have 29 newtons. So let's go to 2. Okay, we calculated that. Oh, okay, so our thinking was correct. Yeah, because they're going in opposite directions. Okay, so we didn't have to worry about splitting this. Okay, that's good. So I guess with torque, it doesn't matter as long as you focus on the central point that you're on. So I guess that works out. Okay, so the next one looks like it's gonna be a tough one. but I did promise you guys a little bit of linear algebra, so we'll probably save this one for next time. But we did work with a lot of vectors though. I'm actually proud of that. We didn't, we did learn slowly about torque. We didn't get this or this right, but, you know, at least we handled like problems that seem more like physics. So, well, these are physics problems here, but the first ones we started with were mainly for vectors, but you guys get what I mean. So I guess this video is going to be like more like physics driven. So now we're going to go into more linear algebra now. So I'm going to be looking up the linear algebra content from basically from the site I use, Udemy. I basically muted my internet browser so for you guys, so you won't hear what if I'm watching a lecture, you won't hear what I'm listening to, but I will be taking notes on stuff, so that way you guys can see what I'm actually doing in linear algebra. So this morning I did relearn the difference between unit vectors and basis vectors. So now the next part they're covering is linear combinations and span. So these are going to be my own personal notes because like they have like they have like a full out document here, but I'm not going to write every single thing in the document. I'm just going to basically summarize what I read. So if you don't see me moving my pen, that's basically me trying to summarize it in terms that I can write on my own. Because there's some stuff I know about the subject, but there are some things that I probably don't have a clear recollection of, and those are the things I'm probably going to write down. So I won't go into a full explanation because like I feel like the YouTube channel is basically my own little archive of like what I do or don't know. And plus, like whenever I do these streams, I always record it, so like just in case if the stream breaks down because my internet's not the best, I still am able to upload like, you know, my journey with you guys, even though the internet kind of crashes on the live stream, so that way you guys can actually see what I'm actually working on. Let's see. Okay, here we go. So definition, span. Span. So according to this, span is a set of vectors which can be represented by some linear combination of the set. Okay. So now I'm actually reading about what a set is, what a span is. So basically I'm trying to like summarize it in my own words so I can better like solidify in my head, because I think span is one of those concepts that I would probably learn about, but I would instantly forget, like, I guess the intuition behind it. So hopefully I will be able to develop an intuitive one sentence to summarize what it is. So from the way it describes it, it seems like the span is using basis components to allow for certain linear combinations to be in the set. Yeah, because they give the example of let's see, where are they? The basis vectors I and j, which you can think of them as sort of like the x and y axis. So these are, and then like linear combinations, such as like if you think about these and like as a vector, you can think of it as like, so like vector v, you can think of it as I plus j. Of course you can't add them together, it's basically like their components. So basically, like if you have one there, it's like, so it's treating like all the, it's like that's the reason why I wrote this. It's like it's using vector basis components to like kind of form like linear combinations of these, and these linear combinations will fit inside whatever it is. Like I want to say vector space, but I haven't gotten to that point yet. I feel like it might be a vector space, but I don't want to assume that yet. So let's see. Okay, so it seems like the way they show it is that the span, or at least like the way to think about it, is that the span involves the basis components. So the basis components basically help make or solidify the space that you're working with. So if we have like R2, then basically the basis vectors are this combination, and then if we have R3, we think of this combination of points. And I'm guessing this is where it talks about like the dimensionality, because like, you know, R2 has 2 and like R3 has 3. So yeah, usually whenever I take notes from a textbook or like from a source, I don't summarize it in my own words, which is not very great for me because I end up forgetting what I write from the textbook. So I guess the stream is kind of motivating me to actually try to formulate the knowledge in a way that I can interpret and go back to, which is the point of what notes are. Okay, now we're getting into span and linear independence. So, oops. So I'm familiar with linear independence. I just have to do more diligence on actually like doing problems involving linear independence. Right now I'm just like reading more in depth about linear, like I guess like linear dependence and dependence. Like they go a little bit more on paragraphs here. So it seems like they're not going to discuss like the difference between linear independence and dependence right now. So they have examples here. So they gave us one example, which is like to prove a linear combination of a basis vectors, and they give us basis vectors, and then to get any vector within a random vector of the space we're working with. So I think we can try to do the quiz. I've done this quiz already, but I'm going to retry it. Okay, so the first question is, yeah, sometimes like when you look at something, you like, I know what linear independence is. It's just that maybe I should write it in my own words. So like, I mean, I'm familiar with like, I guess like the workings of it, but like I guess defining it is probably like charter. Because the way I'm thinking of it, I'm thinking of examples, but mainly like you want like so if you have a combination like this, like so like basically we have like each component, but each component is like completely different. But if you had something like this, something like that, you would say that this is linear dependent because all of these can be divided by 2. So you would have like something like I, and then 2j, and then this is supposed to be k, and then 3k. So it's like basically like that. And hey, Ursula, how's it going? What's the best part of your day so far, my friend? From the way I understand it, it's like this part would be linear independent, but like this wouldn't, because it's dependent on 2, and it's kind of like an even number proxy of this. So that's the way I kind of understand linear independence. And you want linear independence like this so that you can just reduce it to its like much lesser version. That's the way I kind of interpret it, but I'm pretty sure because they said they're going to explain it in the next section. So so question 1 for this, I guess this prompt here: how many linearly independent vectors are needed to span R4? Okay. I think this one's an easy one, because I think it's 4. Because we saw that with R2 you need 2, and with R3 you need 3. So I'm going to say it's 4. Yep, that's correct. Alright, so next question. That's correct. Will the vectors... Oops, see. Had a stressful shopping today. Was walking around for like 8 hours. Oh, wow. What were you shopping for? Is it is it gonna be a celebration or someone's birthday or something? Why were you walking around for 8 hours? You traveling or what's up? Okay. So will vectors span like I was discussing before with linear independence, I noticed that vector v is basically not linearly independent. It's basically linearly dependent, because if you multiply 2 by u, it's literally like u times 2. So helped a buddy of mine choose a sound system, then went to a big retailer out of town. Oh, I see. Yeah, it's like one of those big like home projects. Okay, so we have like so it's multiple choice, but let's see. Will the vector span R2? So like for A, it basically says yes, the vectors aren't parallel. Yes, because the vectors are parallel. No, because the vectors aren't parallel. No, because the vectors are parallel. So now I gotta think about what it means to span. So I think span, in the definition, it has to be linearly independent. I believe so. Because if it's not linearly independent, it's practically like not part of the span, I believe. So I know that these two are definitely parallel. So we already established that these two lines are parallel. The question is, because I think a span has to be like, basically it has to be linearly independent, and since V is not linearly independent, it's literally just u times 2. I think the answer is going to be D. No, because the vectors are parallel. Span is the set of all points able to reach by adding multiple vectors of these. So we know that both lines are parallel, but they're not on the same line, though. So I don't think both vectors will span in this case. So let's go. I'm gonna go with my first choice, and let's. So it's no. The vectors are no, because the vectors are parallel. So since they are parallel, by adding all of those lines, you will only ever reach points along a line. Let's see. Okay, yeah, we got it correct. Nice. Yep, no, because the vectors are parallel. Okay, cool. So I was kind of doubting my knowledge there for a second, because I was like, because when I'm thinking span, I'm thinking of a plane, and I'm like, no, I can't think of a plane. It wouldn't be right to think of a plane that way. Like with a span at least. Okay, last question. Okay, so the last one is, can the standard basis vectors span of a set of vectors can also be a line, a plane, 3D space. Doesn't have to be a plane. Yeah, no, it's just in my head. Like I visualize it as a plane. I know I know it's not just a line, a plane. It can also be a line, a plane, and a three-dimensional space. It's just for me, like the default way of like looking at it is through, it's like a plane in my head. Like I think of like a tapestry, and like the lines like in it, like it reminds me of like, you know, like lines from like, you know, like a graph. Like if you're thinking of like a blanket, and it's like all the knitting, like the knitting is like just linear lines. If that makes any sense. Okay, so I definitely know the answer is yes, they can span. Because okay, this is easy. We're gonna go with yes, because the three are linearly independent vectors of R3, and will span R3. Let's see, because I know they will span, so yes, we got that correct. Nice. So we got that one correct. Okay, cool. So I felt like I was very behind with linear algebra, like, but relearning it, it's like, it feels like, oh, okay, it's not as challenging as I thought. So, but that doesn't mean I know it. It just basically means that like getting the muscles to get back into linear algebra is, it's not as hard as I thought it was gonna be. Okay, so this one is going to be linear independence in 2 dimensions. Oh. think the last part of stream is just basically going to be basically learning more about linear independence. Dependence, a vector that can be written as another vector with a scalar multiplied to it. I mean, that's the best way I can summarize a linear dependence. And when you think of like linear independence, it's like the opposite, where it's like a vector that can only be written by that combination of numbers. So maybe we should write that for you guys at home. Linear independence vector, or maybe I should write linear combination. Linear combination. Why'd I write component? Combination that is unique. To summarize that, it's basically like, you know, like if you have like one example would be like if you had v as a vector, and then v is equal to 1i plus 2j plus 3j, I mean 3k. So if you had that, like if you had like basically like this this combination here, this would be linear independent because obviously we have like two prime numbers, so they don't reduce to anything. But if you had like a number that's like u, and basically it's like 2i plus 4j and plus 6k, obviously you know that that's basically like that's dependent, because you can just write that as like u is equaling to 2v in this case. So that's the best way I can think of it. Yeah, actually that might be better though. Irreducible, yeah. I think I just didn't think of the word right away, because I'm trying to create my own notes and like because I know what you're saying though. I know what you're saying. That's probably a better way to phrase it if I was like teaching it to someone. It's like irreducible and all that stuff. Because in my head I was thinking of prime numbers, and I'm like, no, it's not just primes. It's just let's see. So they go over linear dependence. Okay, here we go. Now they're talking about spanning. Right here. So, let's see. Spanning. Well, actually, I should rewrite that. That doesn't look legible at all. Spanning. it seems like they're giving an example of like linear independence. Oh, here we go. So we didn't have to really write that much about spanning. So, testing for linear independence. Ooh, this one's something I probably should pay attention to. So, testing for linear independence. Actually, Ursula, we were doing like a couple of physics problems on torque, like before you came in. Because I know you're also into, I know you really love physics. I still have to do more on torque though. I didn't realize it was like in the book I was using, it was chapter 10. I thought it was much earlier than that. Because I thought it would be like much earlier because I didn't realize it was after potential and kinetic energy. But then again, I still am lacking details on all these. What's after that? Equilibrium and elasticity. Yeah, I'm just like unfortunately I read slowly, so I'm just like trying to like look at these like predominantly a little bit quick so that you guys don't feel like you're just watching me like not write anything. I did learn like one of the problems I did here, because I got two problems involving torque wrong, and I was like wondering why. Like this one, it doesn't give you an angle, and I was like, oh, do I have to assume an angle or something? And apparently it's asking how do you maximize it, and I realized, oh wait, you have to have this at 90 degrees. So what I lacked in this one was basically the mathematical behavior. I understand. Like I was looking at it from a visually I saw the physics, I guess like the physical way how to interpret it, but I didn't pay attention to the mathematical behavior. And then I think for this one it's the same thing because I got the angle incorrect, because the angle here is not the angle you use for the problem. You have to actually do some like you have to actually fiddle with the angle. Because I think the angle is like 71 here. And I had to think about it. And I was like, oh, the angle between the forces. And I was thinking, and this angle is with the horizontal, not with the arm here. We had to get this angle, not this angle. And that's what I learned. And I think over here we kind of like applied what we learned and tried to like do some simple problems here. And then further on, I tried to do this problem. And this problem actually got me a little stumped at the beginning, because I was worried about this little point here. But then I thought about it, I was like, wait, so this force is going down and this force is going up. So I was thinking that the total torque was basically these different torques, and you just basically reduce, since they're going different directions, you have to subtract them. And since that this one is probably going to be the higher torque because of, since it's at 90 degrees, I thought you had to reduce this torque. And then, yeah, we managed to get it right in this part. So I would have to say that's what I learned from about torque. I don't think that's a lot, because like we didn't do any complicated problems, but it's like just a little bit of the basics. Let's see, how much do we have here? Oh, this document's pretty long. Let's see, testing for linear independence. Okay. so the way it looks like they make the test look like is that it's like they have you solve a system of equations for each scalar in front of the basis vector and solve for those scalars if the scalars are equal to 0, then oh wait, hold on. Solve the linear for each scalar in front of the basis vectors and solve for those scalars with the equations equaling 0. Yeah, because I think they set it up with like 0 on like at the equal sign. If the scalars equal 0, then the vectors are linearly independent. What's another way you could think of a test for linear independence involving angles? Involving angles? That's a really good question. Probably gonna have to ponder that for a while. Well, I think that will do it for today, guys. It's like already 4, but thank you guys for joining me today, and for anyone that's like that came in like midway, thank you for stopping by. I will put if you like math, physics, or just basically a study stream to keep you productive, you know, be sure to drop me a follow if you're watching this on Twitch. But if you're watching this on YouTube, you know the drill. If you want to keep up with my content, drop a comment, like, and subscribe if you want more math and physics content. So let me just type up Discord for those in chat, as well as my YouTube channel. So in case you guys ever miss any of the live streams, you can come here, or, you know, like if the live stream is just like very buggy, I will always record the live stream, so that way we have the better version uploaded on YouTube. And I also will put up my game channel, my video game channel, if you want to check out me playing video games. So that's another thing you can check out. But yeah, thank you for joining me today, guys. And always remember, oh, what did you type in, Ursula? Another hint, what's 3 angles between linear independent vectors? Oh, I believe that they're orthogonal, aren't they? Unless that's like one of the ways that they can be linear independent, though. Because I always remembered that I always remember, like, you know, the basic ones, like, you know, I, J, and K, they're all 90 degrees. So I'm trying to think about all the basis vectors that are out there, like, because usually when I think of basis vectors, I think of like vectors like constantly like in a mess, but Yeah, but like the thing is that like isn't that just like one type of like linearly independent scenario? Because like when you have a span of vectors, right, even though they're linearly independent, does that mean that they I don't think they always be 90 degrees, right? You can always like have them like twist and curl and, well, not twist and curl, what am I talking about? This is linear algebra. I mean, can't you have them at different angles? Like, and it doesn't have to be exactly 90 degrees? That's my question. Because I feel like you can. Like you can have one that's like 20 degrees, and you can have one that's like 30 degrees, and you can have one that's like 60 degrees, right? They don't have to be orthogonal, but you can reduce them to an orthogonal basis. Okay. That makes sense. That makes sense. I don't think we gotten that far yet. So, that's probably something I have to keep in mind when I'm actually doing linear algebra on the side. Whether it be on stream or whether it be outside of stream, because you know sometimes I feel like my brain is restless and I actually have to learn more linear algebra, or like I feel like I have to actually do math a little more. But yeah, but thank you guys for joining us today. All the links will be in the description down below, and always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream. So take care, guys. Bye.